Hello, everyone. Uh, so today I'm going to talk about how we do computer vision data-centric workflows at Snorkel and how these workflows can help us go from millions of noisy labeled images to accurate models in a matter of minutes. And this is work done by my entire team. So a lot of what you're seeing will not be possible without their efforts. Damian, Hamza, and Vivek have been working on this for the past 1 year or so. So today, I'm going to give a brief background to start with on like what data-centric workflows are and how we think about them at Snorkel. And then I'm going to talk about weak supervision for computer vision with foundation models and show a brief demo of how these workflows come into life when you combine foundation models and do computer vision workflows. And then close out with showing real impact these workflows can have by showcasing results we did with a design partnership with Wayfair. So here is a diagram that kind of shows the workflow that we think at Snorkel is possible, in the sense that typically what we have noticed over time is models and infrastructure for a lot of tasks have become pretty much commodity. And a lot of the bottlenecks in deploying models have come to the data. So preparing the data to be used by these models and having it in a shape form that you can quickly train models and analyze them. So this is the loop we focus on at Snorkel. And a core piece of what we do is make that data supervision and preparation fairly easy. So what we aim to do is make that process, which is very tedious and manual, and scale it up by 10 to 100x. So how do we go about doing that? So when we think of this programmatic labeling is a core piece of our thinking, we think of labeling functions. So these labeling functions operationalize organizational knowledge you have for AI. So what should you think of when you think of these labeling functions? These could be straight up manual labels that you already have, or rule-based systems or subject matter expert knowledge that you have within the organization that can be expressed in different ways. More recently, you can actually use more advanced labeling functions based on large language models like GPT-4 or multimodal language, just like multimodal models like CLIP, which is what will be the focus of the talk today. So what we essentially do is take these labeling functions, which enable you to label programmatically. So let's take a look at what labeling functions look like for text before we go into what makes them different for computer vision. So here is a small example. So you have this small message you might have gotten sometimes on your phone, which says, hey, you have won a gift card from Walmart for $1,000. Please fill out the form link below to reclaim the gift. And once you have a message like this and you want to see, okay, I want to flag these kind of messages as spam, you can try writing labeling functions of the following form, right? You can say, hey, maybe if the message has a keyword gift card, probably it is spam. Or you can also write regular expressions like, okay, if it has a dollar amount, probably it is spam. So as you can see here, labeling functions on text data can be specified as patterns on words, and it's a very natural interface for humans because we speak language and we understand language. But when it comes to images, things change a bit. So let's say you want to build a model to identify the bananas, if an image has bananas. So you can think of like, okay, how do I express this? You can say something like, hey, maybe pixels or patches which have yellow might be a banana, but you can quickly see how that fails because there are a lot of images that match the description. This is just because of the variance in these images. And even if you use some other high-level features like edges and contours, you will end up with the same problem. So the main challenge here, it is hard for a human to describe labeling functions on low-level things like pixels or patches for computer vision. So how do we get around this? So there has been a lot of recent work on learning representations which combine both language and image using internet scale data. So this is a figure from CLIP, which is a model that OpenAI released, which kind of does this. So what the key idea here is you take text and images which co-occur on the internet, and you encode the similar pairs. For example, here is an image of a dog, and there is a text caption associated with it. You encode both the text and the image. And what you try to do is build representations where both these are closer and unrelated pairs of image and text are farther. So by doing this at scale, I won't go into the details of how this actually works, but by doing this at scale, you now enable an interface between natural language and text. So you can now get a wide understanding of what is on the internet, as well as enable a natural language interface. So what does this enable us to do? So you have labeling functions. Now you can ask questions like, hey, can you find images similar to this particular image? Or now you can say, hey, is the particular patch in this image similar to what I'm looking for? Or you can even directly interface with your data using text. And all this is possible because of foundation models like Clip, right? So once you have these models, I will go into a little bit of details on how these work, how these labeling functions will work in the demo. But once you have these labeling functions, what Snorkel does is you can take these labeling functions and get some denoise labels, and then you can train an end model based on these labeling functions. And note that these, even though these foundation models are great, they are not going to be accurate, and you actually need this kind of denoising and iteration, as we'll show in the demo. So once you have built a model, so what you would do, you would take that model and you can analyze the errors that the model makes. Typical errors like misclassifying things or not making classifications on things which should be classified, like false negatives. And once you have this loop complete, now you can again go and explore more of the data and figure out the failure modes. So Vivek will present it. So let me switch to a demo of this workflow and how this works in real life. So let me share my screen. Yeah.
Hello and welcome to Periscope. Periscope is an application developed by the Snorkel research team, which is used to do image classification. So today we're going to show you how our typical image classification workflow happens. And for this particular example, we're going to use the DOTA dataset, which is a satellite image dataset. So the first thing that we probably want to do when we've loaded up a dataset is to go ahead and take a look at what the images look like in this dataset. So to do that, let's head over to the UMap component. The UMap is basically a two-dimensional projection of a small subset of your data. So we can select different parts of this by using the box select. So let's explore this particular region of the data. And let's see, okay, a couple of satellite images here. And we can just scroll through this gallery to kind of get an understanding of what these images look like. So basically that's what your images look like in the DOTA dataset. And let's say that today we're going to be interested in the harbor category. Essentially, we want to develop models that can detect if there's a harbor in the satellite image or not. So the first thing that we probably want to do is understand what harbor images look like. So to do that, let's head over to the Analyze page. The Analyze page deals with the validation set, which of course is hand-labeled and annotated. Let's go ahead and see what harbor images look like so that we gain an understanding of what kind of images we are interested in. So let's do that. There we go. So these are harbor images that have been annotated in the validation set. As the name is pretty obvious, we can all understand why these are harbor images. We can scroll through all of them so that we get an understanding of, okay, there's clearly a boat here, there's a harbor, same thing over here, some boats, harbor. Essentially, the reason we're doing this is so that we understand what kind of images we are looking for and what we're interested in, so that now, when we head back to the Explore page, where we're dealing with the large quantity of unlabeled training data,
Ravi,
we know
Teja,
what
can
it
we
is that
turn
we're
the
looking for.
volume up on the video?
Let's see if we can do some hand annotation. So essentially what we're going to do here is that scroll through a bunch of images, and we're going to say whether they are harbors or not. Obviously, this image has no harbor in it, so we'll say it's a negative.
Is it not audible at all, or the volume is low?
It's very, very quiet.
I see.
When you shared, did you optimize for sound?
Yeah.
Okay.
Yeah. It says, let me try it again.
Hello and welcome to Periscope. Periscope is an application developed by the Snorkel research team, which is used to do image
I think
classification.
that's a little better. Thank you.
So today we're going to show you how our typical image classification workflow happens. And for this particular example, we're going to use the DOTA dataset, which is a satellite image dataset. So the first thing that we probably want to do when we've loaded up a dataset is to go ahead and take a look at what the images look like in this dataset. So to do that, let's head over to the UMap component. The UMap is basically a two-dimensional projection of a small subset of your data. So we can select different parts of this by using the box select. So let's explore this particular region of the data. And let's see, okay, a couple of satellite images here. And we can just scroll through this gallery to kind of get an understanding of what these images look like. So basically that's what your images look like in the DOTA dataset. And let's say that today we're going to be interested in the harbor category. Essentially, we want to develop models that can detect if there's a harbor in the satellite image or not. So the first thing that we probably want to do is understand what harbor images look like. So to do that, let's head over to the Analyze page. The Analyze page deals with the validation set, which of course is hand labeled and annotated. Let's go ahead and see what harbor images look like so that we gain an understanding of what kind of images we are interested in. So let's do that. There we go. So these are harbor images that have been annotated in the validation set. As the name is pretty obvious, we can all understand why these are harbor images. We can scroll through all of them so that we get a understanding of, okay, there's clearly a boat here, there's a harbor, same thing over here, some boats, harbor. Essentially, the reason we're doing this is so that we understand what kind of images we are looking for and what we're interested in, so that now, when we head back to the Explore page, where we're dealing with the large quantity of unlabeled training data, we know what it is that we're looking for. Let's see if we can do some hand annotation. So essentially what we're going to do here is that scroll through a bunch of images, and we're going to say whether they are harbors or not. Obviously, this image has no harbor in it, so we'll say it's a negative. Next image, obviously, I can't see any harbor here, negative. Let's go to the next image, no harbor here either, negative. Let's try and see if we can explore another cluster and see if we can find some harbors. Okay, so we selected another cluster. It looks like there are no harbors in this cluster either. Negative, nope, not a harbor, not a harbor, not a harbor. So this is where the problem begins. We're trying to look for harbor images which we can label, and we can't seem to find any because there are just hundreds and thousands of images. So what is a better way to search through our images and find the kind of images we're looking for? To do that, Periscope has LFs, or labeling functions, and we support three different kinds of labeling functions: image LFs, text LFs, and model-based LFs. Let's explore what text LFs are. Text LFs require you to input a text prompt or a text search query. We are interested in harbor, so let's put harbor, and let's click Create Text LF. And notice that we got this neat little histogram over here. So what just happened? Essentially, the foundation model took in our text prompt, which was harbor, and converted it into the embedding space. Now we have already pre-calculated the embeddings of the entire data set images already. So now given our text prompt embedding and our images embedding, we performed a similarity search. And we display the results of that similarity search in this histogram here, where images to the rightmost region of the histogram should be very similar to the harbor text prompt. As you can see, these are indeed harbor images. And conversely, images on the leftmost region of the histogram should be very dissimilar or unsimilar to the text prompt, which is harbor. And as we can see clearly, there are no harbor images here. So let's go ahead and create our text LFs. We're going to set some thresholds. Essentially what this is saying is that any image that has a similarity higher than this, a score over here, we're going to say it's a positive or belonging to the harbor class. And conversely, we're going to set this as a negative. Notice it turned red. Essentially what that means is that any image to the left of this score or lesser than this score, similarity score here, we're going to label it as negative or not belonging to the harbor class. We'll call this our harbor text LF, and let's hit save LF. So we notice a couple of statistics that just appeared here on this table. This is the positive precision, negative precision, positive recall, and negative recall. And it's important to notice that these metrics are calculated on the validation set because we only have annotated data for the validation set. Our positive precision is 1.0, which is obviously very good. but our positive recall is just 0.07. Let's see if we can increase our positive recall, as in get more harbor images. To do that, we'll slightly loosen this up, and now hit save. Much better. We have a recall now of 0.12. So now that we have an LF, let's go ahead and actually train a model. So let's go to train. We'll use our harbor text LF. And the first thing we have to do is create a label set. So we'll call this the harbor1 label set. And we'll select GT labels. And now we're going to hit generate labels. And what's going to happen is our label model is going to take our LF, apply it, count, and return a label set. And we can use this label set just created over here to actually train a model. We'll call this M1. We're going to be training on the harbor class, of course. And let's hit train. There we go. We got our first model. We have a val F1 score of 0.48 and a test F1 score of 0.46. Now that we have trained the model already, let's go ahead and head over to the analyze page where we can analyze the model, see where it's doing well, see where it's not doing so well, and see if we can improve our model. Let's go to the analyze page. And the model we're interested in, of course, is our M1 model on the harbor class. And let's look at our model's false negatives. Essentially, these are images that our model has predicted as not harbor when indeed they are harbors. And let's click apply filter. Looking at the images, it becomes fairly obvious as to why these are false negatives. All these images are indeed harbors. You can see the harbor here. In this image, you can see a lot of boats as well. Let's go to the next gallery. Same thing, there are houses here, but these houses have a harbor attached. Same thing over here, houses here, but the houses have a harbor attached. Let's keep scrolling, more images. Clearly, there are harbors here. When you go through these images, you get an understanding as to what the pitfalls of your model are. Looking here, we understand that there seem to be a lot of images where there are houses with attached harbors, but our model for some reason is saying that these aren't harbors, but obviously they are harbors. So now that we know one of the modalities of failure, let's head back to the Explore page and let's try to see what we can do. Let's write a model-based LF. So let's go harbor and let's click create model-based LF. Essentially what we just did is we took our M1 trained model and we allowed it to predict on the entire training data set. And then we organized that prediction into a histogram where images to the right here are positive and images to the left are negative based on the model threshold. And let's investigate this region over here. Essentially, this is the region that's going to be very close to the classification boundary. Let's look at what kind of images are in this region. Okay, so one of them is actually an image that is very similar to the modalities of failure that we have, images that have a house in them with an attached harbor. So let's use one of these images to write an image-based LF. So we're going to use this image, we're going to say view as image-based LF, and we're going to say create image LF. Once again, we got a histogram. So what just happened? So we took our image here, converted it into the embedding space, and then performed a similarity with the rest of the training data set, and we displayed the results of that similarity in this histogram. What should happen is that images to the right over here should be very similar to the image that we just have. Yep, indeed they are. And images to the left of the histogram over here should be very dissimilar to the image that we just gave as input. Yep, no harbors here. Let's go and set some thresholds for our image-based LF. Negative threshold as well. We'll call this harbor, and we'll call our LF harbor image LF, and let's hit save. Notice here that it says our positive precision is 0 and our positive recall as well as 0. Essentially what this means is that we aren't capturing any of the validation data yet. So let's make this a little lesser, and now let's hit save. There we go. Now our positive precision is 1.0 and our recall is 0.04. Now we've written an image-based LF that basically addressed a mode of failure in our previous model. So let's go ahead and train a new model. Call this, we're going to use both the LFs that we have created. We're going to call it the harbor2 label set, and let's hit generate labels. Our label model has created our labels in harbor2, and now we'll call this M2. Let's hit train. There we go. Our new validation F1 score is 0.7, and our new test F1 score is 0.68. So over a 20-point jump in F1 score. Thank you.
So hopefully Vivek's demo has shown you how this iteration loop works and convinced you that, hey, you can actually quickly build models. But let's switch gears a bit and see how this model building can work at scale. So we did this to pilot this workflows. We did this design partnership with the Wayfair team, Archana, Tulia, Vinny, and Leshan, and they have been amazing to collaborate with. And most of the results you see here wouldn't have been possible without their collaboration. So what was the problem we were trying to tackle here? So Wayfair has this product catalog, which is like millions of images, and some product images look like this. And they have different products that are listed here, like sofas, pillows, or whatnot. And they essentially want to extract information from these images on what these products, attributes of these products are like. Hey, what is the kind of this sofa? What is the color of the sofa? What is the arm type? So on and so forth. So they want to build models to cover thousands of these product tags, and they want to make this happen because customers typically search for all kinds of attributes when they're searching the product catalog. So the first thing the Wayfair team realized is like, okay, manual labeling workflows for this kind of effort are not going to scale. So for these product catalog images, there are some supplier label provided labels. So these are labels that suppliers add when they upload the product to the catalog. But what they noticed is that the supplier labels are noisy, inconsistent, and sparse. So they don't necessarily cover all the edge cases that they want to cover. And it also creates friction in onboarding suppliers, because you don't want people answering like 1,000 question form on when they're onboarding their product. And it's also difficult to meet quality standards overall because of these two constraints for extracting products with those, building models to extract products with those labels. And the other option is manual data curation, and it has extremely slow startup time, and it is extremely time intensive. So it just took 8 weeks to label just 6,000 images just to create a validation set for evaluating some of these models. And it would take person years to label these data sets at scale required for VIE. And it's, of course, going to be extremely cost intensive, running up to millions. And overall, this was a no-go because the whole process is slow and expensive, and it is not feasible to deliver the models that they want to. So we did this design partnership where we wanted to assess the impact of these kind of data-centric workflows on high-value and representative tags. So we took these 5 diverse categories, which represented a lot of the high-priority product and media tags. This data set was about 4.2 million images, and it had some noisy and sparse supplier labels. And we applied Snorkel's data-centric workflows to this, the workflow that we have shown in the demo, to this data. So the results were that we could actually build substantially more accurate models relative to models built using supplier label baselines, as shown here. So the x-axis here is models built for different kinds of tags, and the y-axis is the F1 score. The red bar is what if you just train models on the supplier baseline, and what if you train models using the Snorkel Periscope workflow. And as you can see, there's a significant improvement. And the important thing to note here is that there is very little manual labeling here, and these are millions of images, and most of them were programmatically labeled. And this is the kind of benefits you get across design pattern, different kinds of tags. So you might ask, okay, so there are modeling improvement gains. So how fast is the iteration? So here is, we did a study where we got a few data scientists and research scientists to build models for a particular product and tag combination. And we asked them to do this in one session. And the x-axis in this plot is model development time in minutes, and the y-axis is the F1 score. So roughly what we found is that people take about 21 minutes to do one iteration of model development, like Vivek has shown, where you start from, hey, exploring your data, trying to build an initial model, analyzing it, and then coming for the next round of writing labeling functions. That about takes 21 minutes. And this is a significant improvement over model iteration cycles, which typically take 3 weeks with manual labeling, where you say, hey, we got some manual data labeled, got a model built, now we analyze the failures, now we send more data to manual labeling. So it really crunches the iteration time. And as you can see here on the y-axis, in about 1 or 2 cycles, you get significant improvements in the F1 score. and model performance. So with that, thank you, and I'm happy to take any questions. Yeah.
Thank you so much, Ravi, Teja. We do have a couple questions here in just a couple minutes. So we'll start out with the first question, which is, how do these ideas extend to detection and segmentation problems?
So like we have computing representations currently at the level of images, but we can actually compute representations within the image belonging to specific parts of the image or different objects in the image. And the workflow would afterwards look fairly similar. So it's about the foundation models which understand more nuanced things, not at the image level, but beyond the image level in spatially. Yeah.
Got you. Okay. In the demo, one thing that was quite noticeable was how interactive both the model training as well as the queries were. How was that achieved?
So the interactive parts are achieved by pre-computing a lot of these representations, and we actually have like a lot of infrastructure built that allows you to fast train these models and also do these queries fairly interactively. So we are interactively querying millions of images and actually training small models on top of those representations fairly. As you have seen, the demo is fairly interactive. Yeah.
And then last question here, what kinds of labeling functions are most commonly proved useful for image classification?
So typically, the way we start is we start with whatever the model already knows, we zero shot it. So the labeling functions that have proved useful are more nuanced things that people want to capture. So for example, let's say you want to capture something like what is the type of the arm. So that's not something a foundation model inherently understands. But now you'd say, okay, maybe it has buttons on it, or maybe it has some furrows on it. You can typically write those lower level understanding atoms, and then you can combine those labeling functions to say, oh, if you combine this concept and this concept, maybe this is the kind of thing I'm looking for. So those kinds of things have been fairly helpful. So things that the model doesn't inherently understand, but it understands bits and pieces of it, so that you can provide that info via the labeling functions. Yeah.
Being able to pull those pieces together.
Yeah. Yeah.
Okay, thank you so much for your perspective on computer vision. It was very cool to see what you've been working on and what's now possible in Periscope. Thank you.
Thank you.